Thank you so much, Sheila. It's great to be here. It's been, I think the last time I did a Friday night lecture was about like almost exactly 4 years ago. So I'm stoked to be back and thank you for having me. For any of you who are going on the field trip in, just 2 weeks now,
Yeah.
I will do my best to make some connections in terms of which, if there's a picture, for example, and we're going to visit that mine, I will try to note that just in case you are registered, just to make some connections. All right. And hopefully everyone can see this.
Yes.
Okay, perfect. Okay, so besides looking like a pretty sweet cover of a geology rock band, this is a picture taken from one of the Sunstone mines that I've done a bit of this, the work that I'm going to talk to you about. And I'll kind of talk about a few different mines, and how I'm going to set this up is because this is in the context of what sunstones, which is Oregon State Gem, as Sheila mentioned, what they can tell us about CRB volcanism. I'm going to kind of break this talk into the first 20 minutes is going to be a CRB crash course, and then I'll spend kind of the latter portion going into sunstones, kind of what they are and why we're studying them and what they can potentially tell us. And I have to say, just because this is one of my favorite pictures, there's a couple people in this picture. So this fellow down here, his name's Chris, and he actually owns this mine. This is the Spectra mine down by Plush, if you've ever visited. And these two fellows in here are actually, I would say, probably the world's best cutters or facetors of sunstones. And once we get into some pictures, I can explain a little bit more about that. But these two, father and son, and they cut and facet these to turn them kind of from rough gemstones that you can find in the CRBs to kind of beautiful cut and faceted, sparkling things that you'd want to put into some jewelry. And this guy up top, he's actually the son. I think he's the youngest person to win an American Gem and Trade Association award. So he was like 16 when he won his first faceting award. So just to give a little context, because there's a lot of people I've met along the way, and it's been a lot of fun. So just kind of quick, a little bit about me. I was interested in geology from a pretty young age. And maybe you look at this and you're thinking, hey, Emily, I think your parents made some questionable choices when you were young, putting you in a baby backpack in a quarry. And that's a fair statement, because the picture on the right was taken just before apparently I fell down a small pile of rocks. So maybe, that led me to where I am today. And the picture on the left, I look pretty happy. This was somewhere in New England, and it was taken in a cave, right? Hard hat looks a little questionable, but both my parents were mineral collectors. And so I got kind of interested in geology from a young age. And before we get into the meat of a lot of this stuff, for any of our geologists in training, a lot of the kind of volcanic compositions I'm going to be talking about are basaltic. And so we characterize volcanic or extrusive rocks based on their silica content and their alkalis, which is sodium and potassium. And so basalt, as you can see with this little yellow field, and corresponds to this wonderful little diagram over here, where basalt has about 50 weight percent silica, much higher temperatures, lower viscosity, which means that these things can flow pretty far distances relative to other compositions of lava. I like to, and if you have trouble kind of remembering that, I like to think if it's low, it'll flow. So lavas with low viscosities can travel much further distances than some others. So, and if you need a quick visualization, if you've seen the blockbuster hit Dante's Peak with Pierce Brosnan and Linda Hamilton, Pierce Brosnan may be better known as Harry Dalton in this movie. And there's the unbelievable scene where they're in this cabin and this lava flow comes kind of bursting through the wall. While that is inaccurate for the movie, viscosity wise, you can maybe kind of give yourself a little bit of a visual. Okay, so I said kind of the first 20 minutes here, I'm going to be crash course into the CRBs. And like Sheila said, most of my focus was in the Picture Gorge basalt. So we'll kind of make that transition because I think it's important context wise to highlight how I even got interested in sunstones and kind of which CRB unit they're found in. So the Columbia River Basalt Group, quick crash course again, this is a vast outpouring of basaltic lava that covered the Pacific Northwest from about 17 to 16 million years ago in terms of the bulk volume that was extruded. These erupted out of large fissures or cracks that were scattered all across eastern Washington and Oregon. And overall, we break these basalts because to make sense, we have to, try to make, anytime we want to make sense of the natural world, we need to classify it in some way. So we break the CRBs into 4 kind of main phase units based on their age, their eruptive location, and most useful is geochemistry because unfortunately for us, rocks don't talk, and geochemistry is the best tool we have to really understand what happened. And in this little schematic, the gray polygon is the extent of the CRB lavas, and the kind of orange elongated polygon kind of highlights the extent of the Snake River Plain to the current location of Yellowstone, which is the body of magma that is thought to feed these eruptions. Why is this important? Well, there's a couple different reasons. And if we look really big picture, the Columbia River basalt is a flood basalt, which is a type of large igneous province. And historically through Earth's history, a lot of large igneous provinces, their eruptive timing correlates with mass extinction events or climatic shifts. And most of them are the result of, they're fed by a mantle plume. And the largest of these was the Deccan Traps, which erupted about 65 million years ago. And if you know your geologic time, this was the KT boundary. This was when the dinosaurs went extinct. And my absolute favorite cartoon from a guy named Nathan Pyle, very sad, but it always makes me chuckle. And, so a lot of times we think of, oh, okay, an asteroid hit the Earth and that was the primary cause of the dinosaurs going extinct. Well, at the very same time, pretty much the largest volcanic eruption that the Earth has experienced occurred. And there is ongoing research trying to figure out kind of chicken and the egg, which happened first. As of just, over the last couple of years, this research has been really ongoing. And the most recent update that I heard is that very likely the asteroid occurred first. But of course, then we start to think about, well, how does that then relate to this large eruption? Could it possibly be that an asteroid triggered the largest volcanic eruption on Earth? And I think that's still very much being debated in the literature. But in terms of why these types of eruptions are important, I think this gives kind of a broad context. But focusing in more specifically on our good friends, the CRBs, I kind of already mentioned these 3 bullet points, and I had mentioned that we break the CRB into 4 main phase units depending on age, eruptive location, and most importantly, geochemistry. But so these 4 different units, the next couple slides, all I'm going to do is kind of go through and you'll just get an idea of these 4 units relatively where they're located. So the Steens is kind of southeastern Oregon, and then activity possibly seems to progress north, although that is an idea that we're thinking more about recently. But the picture gorge basalt, if you looked at those last couple slides, the picture gorge basalt, which is here now kind of this black polygon in the center of Oregon, this has kind of been the runt of the litter. It's been considered a little bit different geochemically, and its spatial distribution and its volume is the smallest of these 4 units. So in terms of research, a lot of focus has sort of been paid more on the Grand Ronde basalt because it's, as Martin Streck likes to say, the big baby. It is the most voluminous of these 4 main phase units of the CRB, and the Imnaha and the Steens. But Picture Gorge hasn't really hadn't had any ages other than some potassium argon ages from, gosh, now almost 50 years ago. So if we try to understand these 4 main phase units and their geochronology, and we try to put them together with everything we know, the Picture Gorge didn't really fit with the rest of the CRBs. You can kind of see here in this little diagram, and I know it might look kind of busy, but what I want to mostly draw your attention to are the ages. So you might notice that, okay, so the Steens down here, about 16.97, and upper Steens, the kind of magnetic reversal, that Steen and Steens, about 16.6, and kind of upper Grand Ronde about 16.2. Cool. The problem is that prior to me starting my PhD, the only ages we had for the Picture Gorge were these potassium argon ages from the early 70s. And the problem is that with a lot of these new ages, which are both argon-argon, which actually date the basalts, and then also some studies from like Kasbaum and Sheen in 2018, they used a more precise dating method of uranium lead, and they actually dated little teeny zircon crystals that are hosted within sort of interbedded tuffs within some of these basalts. And those ages are really, really good. So the question, obviously, is these ages don't make sense with what we know now. In fact, they're almost, in some cases, like 1 million years off, which is pretty significant when you think about these ages as a whole. And the ages that had been done, these potassium argon ages on the Picture Gorge, had been done at the type locality of Picture Gorge. So if you've ever driven across Eastern Oregon and you've kind of headed toward John Day, Picture Gorge, there's about 18 lavas, and these ages are from the lava flow at the very bottom and the very top at the type locality. And we do stop there on the field trip. So remember maybe some of this if you are attending. So I mentioned that the only ages for Picture Gorge are these potassium argon ages, and they're from the type locality at Picture Gorge. But the uncertainties on these, as I said, they're pretty big, 0.8 million years. And if we think about the fact that, they're supposed to be, according to more recent studies, about 16.2, these are, way off. So we definitely wanted to revisit this, and it begs the question, how does Picture Gorge sit in with the rest of the CRB in terms of stratigraphy? Well, there was a study that tried to unravel and learn more about this, and instead of analyzing new ages, they took basically the old raw data from this potassium argon work and tried to calculate an age using kind of updated standards. And it sort of worked. I think it's received a decent amount of criticism, but it slightly changed the ages of the Picture Gorge from 15.9, 14.7 to a little bit older. But this study has been kind of, there's been a little bit of criticism just because, again, these ages weren't new. It was just sort of recalculated. And if we think about the fact that at Picture Gorge, the magnetic reversal that is recorded in the sort of magnetostratigraphy is supposed to represent N1, R2. And really all that means is that the bottommost flows are normally magnetized and the uppermost flows are reversed. So based on that and these potassium argon ages, this N1R2 has thought to be sort of the extent of Picture Gorge in terms of time. But where this work was done at the type locality, beautiful section exposed, but the Picture Gorge is much larger in terms of extent. So, do these ages, these potassium argon ages, they don't jive with the more recent ages we have for the CRB. And it's restricted to kind of one place. And my PhD actually sort of came about because much further south than the type locality, which is denoted with this little blue star there, my PhD advisor, Martin Strack, this was now 10 years ago, was doing some work with other students around the Malheur Forest between the bustling metropolises of John Day and Burns, and came across this, textbook, beautiful dike.
Yeah.
And he grabbed a sample and got it analyzed and was, I think, pretty surprised to see that geochemically, this was sort of as he says, a dead ringer for Picture Gorge. It wasn't Steens. If you remember, the Steens are kind of located further south. So, if you see a basalt in this area, and you do have some potentially stratigraphic control, that it's mid-Miocene, your main players for the CRB would be Picture Gorge or Steens. So he was pretty surprised to see that it was Picture Gorge, and that was sort of the main motivation and the catalyst for me starting this work. And so there were a couple, as I said, motivating questions, and it had to do, one, with the spatial extent. So if there was this dike of Picture Gorge located pretty far south from the type locality, where else is Picture Gorge? A lot of these basalts in these areas, sometimes they're just kind of broadly mapped as CRB or mid-Miocene basalt. But if Picture Gorge extends pretty far south past the type locality, it also kind of plays into, when did the Picture Gorge basalt erupt? We already know the potassium argon ages aren't, they're not robust and they don't jive with the new ages, but it kind of adds another layer to the problem. And so it was, what is the eruptive timing of the Picture Gorge? When I started this project, basically I went out and I sampled a bunch of locations, and from those kind of targeted a few based on their location, and also sometimes how fresh they were. But eventually I had about 14 samples that I dated with argon-argon. And most of these samples have been dated, well, actually all of them have been dated 2 or more times. Some of them have actually been dated like 15 times because it's part of some ongoing work. So of these kind of samples, and these are the little black dots on this map, you can see that a lot of them extend farther south from the Picture Gorge and how it was mapped, right? So this darker polygon in here being kind of the extent of the Picture Gorge, and most of these little black dots in here are further south. But before we dated them, I wanted to make sure, are these in fact Picture Gorge? So I looked at a couple different geochemical plots, and there's a lot going on geochemically. So really all I want you to note is that the black dots on the right, the 3 little panels, overlie kind of the gray circles and the kind of open circles, which are picture gorge, either from previous work or from some of my earlier work. So we felt pretty confident that these 14 samples here were in fact picture gorge relative to Steens. And hopefully I can sell you on that, and you can see that all these little black dots on these geochemical plots lie much more comfortably on the gray dots than the red, which represents Steen. And of those 14 ages, I'm only going to highlight 3 here. And of course, I'll be honest, I'm highlighting the best ones. So of these 14, there are 3 that I kind of show here, and these are age spectra, age plateaus from argon-argon work. And I have, 16.22, 16.88, 16.96, and these are all pretty good plateaus. If you want to know more information about age spectra like this, we can definitely talk about it at the end. But what's really cool is that these are much older than the original potassium argon ages and older than those recalculated potassium argon ages. So this kind of totally flipped the script of what we thought of in terms of picture gorge basalt eruptive timing. It's older and it erupted for a longer period of time. Some of my ages, like for example, this one, 15.76, this was pretty young. But even, 16.02 all the way up to 17.23, I put these in order here from youngest to oldest. So this is much older than we thought. And this means that the picture gorge basalt actually erupted for longer than any other of those main phase units. I'll say that that is something that we published, and there are definitely folks that, especially people that have worked in this area or on the CRBs for a long period of time. There are some portions of this we're still kind of discussing. And I'm not going to talk too much about this other than this kind of, as we sampled much further outside this original mapped area of picture gorge, which is this dark gray polygon still, we tried, and this was really challenging, and honestly, it's still ongoing. This is a figure from a paper that I have in review right now, and with all these additional samples that we have outside of this original picture gorge extent, especially really far as you get past Burns, if we try to make sense of it relative to the original stratigraphy, like at the type section, things get really complicated. So right now, trying to understand how a lot of these samples that resemble picture gorge basalt in terms of their geochemistry, how they fit into the already established stratigraphy at the type locality is really confusing. And so this is something we're still working on, but it also kind of makes you wonder, if we have picture gorge extending across 100 kilometers further south of where it was originally mapped, could it be that these were actually exposed in other locations, but maybe they've been removed from erosion over millions of years? And I'm going to skip this one because I can get really into the geochemistry and I don't want to go down a rabbit hole. So in terms of this is kind of wrapping up the end of this first portion. Out of kind of my PhD, looking at the picture gorge basalt of the CRB, a couple of kind of main findings. One being that we had this much longer age range for picture gorge, and it was older than all of the other CRB units. And anything in italics here was kind of something that a new area of study that came out of some of these conclusions. So out of basically getting these, compiling these ages, a new method to prep samples for argon-argon geochronology came out, and this is a project that hopefully we'll have submitted as a paper in the next couple months, and this is with some colleagues at Oregon State and at the Argonne Lab that's run by Anthony Coppers. Another thing that came out of this, which is super cool, I'll try not to get too distracted by it, but what I noticed in these 14 ages is that you'll see in this little kind of strat column, and these little black dots on the strat column are basically the same 14 samples that I showed you on the map and that I showed you kind of ages for. Well, if you look at ages in a table, right, and you just kind of stare at some ages, there's patterns are going to be a little harder to identify, right? Like you can definitely figure out, okay, here's the youngest age and here's the oldest age, but patterns in terms of how your ages are distributed may not be obvious. And what I thought was pretty cool is if I look at all my ages, I actually have this interesting gap in the middle. And I looked at other CRB units, and I think it exists as well, which is pretty cool, but it definitely opens a can of worms. So it begs the question, you know, were the CRBs erupted in one big pulse, or potentially did you have two eruptive pulses that were separated by about a 0.4 million year hiatus? And this is something that is still definitely ongoing. I had mentioned the eruptive duration was longer than any other main phase unit. Super cool. That's definitely new, except it doesn't jive with what we know about magnetostratigraphy. And this is something that is hopefully, it's supposed to start this summer with someone who, a PhD student who just finished over at Caltech and is working on this for part of his NSF postdoc work. And, you know, thinking about the spatial extent of Picture Gorge and how these ages jive together, it makes us wonder, well, how did these CRB eruptions progress? If you remember in the very beginning, I kind of showed you that cartoon where if we think about Steen, Zimnaha, and Grand Ron, it looks like you have this kind of overwhelming northern progression. But as we extend spatial distribution of the Picture Gorge, combined with you know, these older ages, this indicates that actually the CRBs started at Picture Gorge or with the Picture Gorge basalt instead of Steen. So it kind of changes how these eruptions spatially progressed. And then, of course, maybe the best one, there were sunstones in the Picture Gorge. And there's been a lot of anything I read prior to doing my own work said sunstones were hosted in Steen's basalt. Well, after about maybe 2 years of going down some literature rabbit holes, I basically figured out that no one had actually done a geochemical analysis on the basalts that host sunstones, which I thought was mind-blowing, right? You just it's kind of like when you're a kid, you assume that adults have it together, and then you become an adult and you're like, oh, no, that's not what's happening. So I just assumed that, you know, there had been some work done and there hadn't. So now I'm going to kind of transition away from the CRBs as a whole. And again, I know that was quick, kind of a crash course. And thinking about sunstones and what they can tell us and what their significance is for the CRBs. So I'll do kind of what is a sunstone, where are they found, which will connect back to the last probably closer to 30 minutes at this point, some previous work and some early findings, and some outstanding questions and hopefully kind of additional avenues to work on. This picture is taken from a mine closer to Plush, so we won't be visiting this mine, but there a lot of the same players are in this picture from that kind of first slide. So I keep talking about sunstones, but I haven't told you what they are, which maybe really isn't fair. Sunstones are, I call them copper-rich feldspar, but maybe that's not the best term because it's not like they're overflowing with copper, but they do have macroscopic inclusions of copper. So essentially, they are plagioclase feldspar that have copper in them. And if you remember from mineralogy, the more specific type of plagioclase they're found in is labradorite. So I like to think about labradorite in terms of compositionally and kind of how it fits in, is if you think of, like a fruit, an apple, and then maybe a specific type of apple. Feldspar is like your fruit. Plagioclase is kind of like saying apple. And then labradorite is like saying Granny Smith. Like it's a really specific type. Just to kind of, because you'll hear me use these words sometimes interchangeably, but just to kind of give you an idea of what it is. And so on our beautiful feldspar ternary, sunstones are denoted in blue here. This is overall their composition. So more calcium rich than sodium. And because of these little inclusions of copper, they can display a variety of different colors, including red, green, pink, and often you'll hear more colloquially schiller, which just means there are, it looks like there's little tiny pennies in there. And sometimes the copper inclusions are disseminated or kind of really small and spread out enough that you can't see them, but other times it literally looks like there's teeny little pennies inside. They are classified by the Gemological Institute of America as a precious gemstone and a hardness at about 6 or 7, so pretty decent for faceting. And where are they found? Almost exclusively, we'll get to that, in Oregon. And so they're kind of, the name is interchangeable with Oregon sunstone. And to give you an idea of what I mean by copper inclusions, this is a picture from Double Eagle Mining from John Aldrich. And so it's pretty cool. John, not only does he own the mine, but he also cuts and facets them himself. So this is, he sent me this picture via text a couple days ago to show me, just because he thought, you could really see how the copper was distributed through the crystal itself. But, you can also see that in here, there are some facets that he's already cut, but just pretty cool. Where are they found? Okay, so this is a map that we've kind of already seen before, but now there's a lot more places on this map. So still our extent of Picture Gorge kind of there in the center. And the most common sunstone area that folks are typically familiar with, because there's a public collection area, is down here in the kind of south of Oregon near Plush. So right in here. And there is another mine that is further north, and that is the mine we'll be visiting on the field trip, and it's very close to Delintment Lake. So to give you, again, thinking about context, most of what we were talking about, right, was the Picture Gorge, except we know now that it's extended further kind of south and east, and there is the Sunstone collection area, and again, public collection area, and a number of claims near Plush, just north of Heart Mountain. And I didn't actually visit that until 2 summers ago. So through the bulk of my PhD, I never went to the Sunstone collection area near Plush. So the 2 main mines are further south, near Plush, near Heart Mountain, and a little bit further north near Delintment Lake, and that's called the Ponderosa Mine. That's the one we'll be visiting with the field trip coming up. So 2 locations, and about 80 miles apart as the crow flies. It does take about 3.5 hours to go between each, even though they're 80 miles, just because the roads between take some time. So as I said, I never visited this southern area. I had only visited this northern area, but I did so kind of out of mistake. It was I think it was the second year of my PhD, and my PhD advisor, Martin Strack, handed me this little green map that he found in basically an issue of GIA's. It was like 1 month kind of, they had an article on sunstones. And I don't know how this kind of came across his desk, but he handed me this map and he was like, hey, you should go check out the Ponderosa Mine. And he said this because Steen's basalt, so right, the one of those main phase units to the south, Steen's basalt are often sort of typified by large plagioclase crystals. Not necessarily sunstones, just large plagioclase crystals. And at this stage, everyone kind of assumed that, well, because of that, sunstones are likely part of the Steen's basalt, especially in the Plush area. That's the closest main phase unit. So it kind of makes sense that, let's assume that most of the sunstones coming out of Plush are hosted in Steen's basalt. And so this is why visiting this northern mine was important, because as we started to extend distribution, if we could show that something this far south, kind of in general, was also Picture Gorge, it was significant. And the fact that it had large plagioclase. So again, when this started, it was mainly just to see, hey, is Picture Gorge here? And what does this mean for kind of mineralogy of Picture Gorge lavas? So this northern mine is where I'm going to focus your attention. And what I did, I just skipped ahead there. I visited this mine. This is the Ponderosa Mine. And, to be honest, I didn't expect much. I just kind of assumed, like, I don't know what this place is going to look like. For anyone who's ever gone, looked at a geologic map or a topo map and seen sometimes the little rock crosshairs and it says quarry, quarry sometimes is like a very small rock pit. So knowing that this was a sunstone mine, I didn't really know what I was going to find. Well, I was blown away when I found, while not massive in extent, pretty much a whole operation. And I grabbed a sample. I chatted with the owners. The owners are wonderful people. Grabbed a sample, and it took a couple months to get analyzed. But what I want to show you is on the upper right-hand corner. For anyone not familiar with spider diagrams, it's no big deal. The only thing really that's important is that the black, which is the black line, these black dots, was the whole rock geochemical analysis for the basalt that hosts sunstones at this mine. Almost, in terms of the other, looking at all of the CRBs, almost perfectly overlies the Picture Gorge. So maybe this wasn't surprising in terms of we had already found basalts this far south of the Picture Gorge extent that matched chemically. But this was more significant because this was a lava flow that hosted sunstones. So what does that mean for the Plush area mines? And sure enough, I'll say it took me another 3 years to get around to do this. What I found was that, from 2 different Plush area mines, that whole rock overlaid much closer to Picture Gorge than to Steen's. And this is pretty wild because sunstones, anything you look at, any piece of literature will say, if it's been, on kind of the area, will say, oh, well, sunstones are part of the Steen's basalt. But there had never been any geochemical analysis to prove that. It was mostly kind of assumed because Plush is pretty close to Steen's. So, you can understand where that assumption came from, but it's just pretty wild now to see that actually the basalts that host sunstones are part of the Picture Gorge. This is pretty significant in terms of not only extent of one of these subunits, but also thinking about how these things erupted, which I'll start to get to. And just a little joke in case you've watched Portlandia, because I think most of us know that Oregonians love our local goods. Oops, sorry. So sunstones were initially kind of recognized to have copper in them like 100 years ago. In 85, sunstones were recognized as the state gem. This high kind of elevated copper concentration was noted in sunstones from Ponderosa, which again is the mine we'll be visiting on part of the field trip. And, there has been some additional work trying to understand some of the coloration, but overall, sunstones are a very unique gemstone and really range in price from about $10 per carat to actually just over $1,000. And they are ethically mined and local to Oregon. And as I said, Portlanders, we love our locally sourced goods, and they're becoming more and more popular across different jewelry markets. This will give you an idea of some of the coloration of sunstones, and these are all from that northern mine, the Ponderosa Mine. But really you can get an idea of how deep red to the green and some of the lighter kind of champagne colors. So these are hosted in CRB flows. And pretty wild because copper should not go into a silicate phase like plagioclase. Okay, so we're pretty sure, that these are picture gorge, which gives us an idea of age, right? Because we already have kind of bracketed the age range of the picture gorge basalt. So, even though in some cases I don't have ages for all of the sunstones, like for the different localities, but by knowing the geochemical signature and being able to correlate to picture gorge, it gives us some idea. But I was lucky enough through my PhD to basically sneak in one sample when I did my dating. And so I got an age for the Ponderosa Mine, again, that northern mine. And the basalt that hosts the sunstones at that northern mine is about 16.2. And this is an age actually that I included earlier. This was one of the samples of those 14 samples from earlier. So cool, great. This totally makes sense. Not only that northern mine is overall does the geochemistry match picture gorge, but the age falls, right in picture gorge timing. Cool. Well, I also tried to date a sunstone, and this didn't work as well as I wanted. On the bottom left, this is an age spectra of a sunstone, again, from that Ponderosa mine. So the problem here, and some of you probably already recognize this, is how do you get a younger crystal in an older basalt, right? Like, how do you do that? You can get older crystals in younger basalts, right? If you had an eruption and it was maybe in training, pre-existing material, but you can't get younger crystals in a basalt. And think about this is almost half the age of the hosting basalt. This doesn't make any sense. I tried dating a sunstone twice, both times getting this kind of cruddy, well, the age itself looks good, right? The spectra looks pretty good. It's pretty flat, but this doesn't make any sense. So this is something actually I'm working on with some people from Auburn University, and I sent them a bunch of samples, and what we're trying to do is figure out if this discrepancy also matches the sunstones down in Plush, because at this point, we don't have a ground mass age for any basalt that hosts sunstones down in that southern area by Plush. the people at Auburn did just tell me that they got their first Sunstone age down at Plush, and lo and behold, it is young. It's like 9 million. So it looks like at this point, we're running into the same problem at Ponderosa and Plush, where the Sunstones are erroneously young and don't make sense with the hosting basalt age. And if you're wondering, well, like, okay, Emily, what if, you had copper that was like moving around in some fluids, and that's how the copper went into the sunstone, and maybe that sort of reset the clock? Well, the closure temperature for sunstones, plagioclase basically, and basaltic ground mass are almost exactly the same. So you really wouldn't be able to just reset one. And anyway, this is a huge question, and I'm pretty intrigued to see where this is going to, what's going to shake out. But sunstones sometimes do have these little fractures in them. So one kind of early thought is it could be these young ages in sunstones actually could be a result of argon loss, which kind of will give us younger ages than we expect. And what's also kind of cool about this, actually, you know what? I'll wait until the end to bring this up. So don't worry about either of the little figures on the right. I'll bring that up as I kind of wrap up here. My mouse is more sensitive than normal. Okay, so we have age, and we know that sunstones are hosted in Picture Gorge, but to me, the elephant in the room is where the heck did the copper come from? Copper should not, I can't stress this enough, should not go into plagioclase. And the diffusion profile doesn't make sense. And what I mean by that is a lot of times sunstones have the deepest concentration of color in the center. And if you just have simple bulk diffusion, you would expect, right, something coming from the outside in, and you would have basically the opposite pattern, that you would have kind of a ring of color with nothing in the center. But we see the opposite. So something that kind of came up was like, well, what if, because basalts do have a little bit of copper in them. What if like the sunstones somehow like sucked in the copper from the hosting basalt? Well, I had a student at PSU, I guess 2 years ago now, Stephanie Welch, who tried to look into this. And so she did some probe work at Washington State University and tried to look at basically a sunstone and the basalt that it was hosted in to see how chemistry changed at that interface. If we saw a pretty staggering difference, you might be able to make the argument that, hey, maybe the copper is coming from the surrounding basalt. But what you can see from kind of this image on the right with all these 6 little plots, this was a transect across basically the edge of a sunstone into the hosting basalt. And what we kind of found was that the sunstone chemistry was incredibly uniform. I mean, wildly uniform. Even the people at Washington State were like, this is wild. We haven't seen something kind of so homogeneous before in terms of like a single crystal. And the ground mass had some variability, but it didn't look striking. It wasn't like as soon as you crossed over, something changed dramatically. And so the kind of results from this didn't give us any indication that the copper is coming from the basalts themselves that host them. So there's basically 2 options that we have for copper and where it came from. One is that the copper went in as the plagioclase crystal was growing in the magma. I refer to this as basically magmatic formation. The other option is that the copper went into the plagioclase post-crystallization. And this could either be kind of at pretty shallow depth or near the surface. And I kind of refer to this option as a hydrothermal process. Still, where is the copper coming from? Not sure. But in terms of method, these are our 2 kind of options that we've constrained. And so you can see these two options here, this magmatic origin or hydrothermal. The problem is that we have evidence that supports both. So what the heck? You know, with a magmatic origin, one of our lines of evidence is that these two sunstone locations, and again, on the field trip, we'll visit the northern one, are about 80 miles apart. So if this was hydrothermal and it is a unique process, you're telling me that it occurred in two locations 80 miles apart, but like nowhere else in the world, right? That seems a little fishy. It is more likely that this occurred at some depth and then, you know, through erupted at two different locations. Also, we have some oxygen isotopes, and oxygen isotopes are awesome, typically at giving any indication of a hydrothermal source. Typically, if hydrothermal alteration is significant, these values are below 5.8 or 6. And the few analyses I've done, they're all over 6. So this also indicates a magmatic origin. Although you could start talking about how long it takes oxygen to diffuse, you know, so that's a possibility. But right now, the oxygen isotope data suggests also magmatic. And there are these really weird types of pyroxene called Protoenstatite that are present as tiny little inclusions. And Protoenstatite is, again, this really weird type of pyroxene that forms at really high temperatures, but pretty shallow or pretty low pressures. So the fact that we have protoenstatite potentially in sunstones, like included as little kind of nano inclusions, suggests that whatever process put the copper there, you know, occurred at very high temperatures, not something that would reflect hydrothermal processes. But hydrothermally, most sunstones are found in like really beat to hell basalt. It's really weathered, you know, and that's kind of unique. And so it kind of looks like it was hydrothermally altered. But I'll point out this is kind of a bias because sunstones and the mines, right? If you own a sunstone mine, you're not going to be like, I'm going to go mine in the hardest rock to drill. No, you'd lose money. Instead, you're going to be like, I want to find rock where sunstones are, you know, the material is friable and I can extract sunstones for cheaper. So it could be a bias that most of the time that we find these, they're in this weathered basalt. But we do have this discrepancy between ages, and also when copper is sort of resorbed, it's lower than the solidus temperature of labradorite. So, and the eruptive temperature of basalt. So it's really tough. It's like we have multiple lines of evidence for both processes, and we really don't know. I'll admit I'm on Team Magma. That to me is more the data we have is more telling that is the origin, but it's definitely the story is not done. And I tried to just include some cool pictures throughout this to make it, I mean, you can just get an idea of how beautiful these things are when they're cut and faceted. So just to kind of wrap up here, I figured it was worth it to just kind of give you an idea of some of the questions we're asking as hopefully this project progresses, and thinking about the age, you know, did copper enter the plage during crystallization? Was it magmatic? Are sunstones zoned in major or trace elements? We can kind of say no, we've kind of already done that. Is there evidence of other economic elements like gold? And the reason actually I'm working with the folks at Auburn is because someone there, Bill Haynes, had done a probe analysis years ago and found traces of gold. So there's a lot of different questions to kind of think about, and I mean, they're beautiful and they're also perplexing. So part of the study that I'm kind of starting to work on or continuing to work on is thinking about the ages, you know, and this discrepancy between the hosting basalt and the sunstones themselves. And thinking about the kind of overall mineralogy and geochemistry of that hosting basalt. and the differences and assess, is hydrothermal alteration a significant process? You'll notice that I have, in addition to some of the sunstone mines in Oregon, I have this random map of Ethiopia. And you're probably like, WTF, why is Ethiopia all of a sudden coming into the picture? I will tell you. In the last 2 years, sunstones have started coming out of Ethiopia. And this is, anytime you're dealing with something with money, there's controversy around this. But what's pretty cool is the proposed extent of where these sunstones, or I shouldn't say the location of the mine that these sunstones are coming from is within the spatial footprint of the Ethiopian Yemen flood basalt. And the CRBs are the youngest flood basalt, but the Ethiopian Yemen is the second youngest. So part of my motivation and thinking about all these questions is wondering if sunstones are actually recording a super cool and unique petrogenetic process that only occurs in flood basalts. And maybe the only reason we see it in the CRBs and in Ethiopia is because these are the two youngest. And so their preservation potential is a little bit better. But I hesitate a little bit when I say Ethiopian sunstones, because there's a whole past controversy of sunstones and where they come from. And this is, rightfully so. About 20 years ago, sunstones from different countries, including China, Tibet, the Congo, Mongolia, started basically flooding the market. And it took a while, a couple of years, for folks to wonder, like, well, these sunstones are here, but like we haven't seen any rough. We haven't seen pictures of the mine. Like, where are these sunstones coming from? And to just break the conclusion to you, it turned out that these sunstones that were flooding the market from these different locations weren't real. They weren't natural. They were taking basically clear plagioclase and cooking them with copper filaments and forcing them to turn color. And there was a study that kind of looked at what would happen if you took clear sunstones from Ponderosa or Plush and cooked them with copper. And sure enough, they turn red, and they look like the distribution of copper looked like a lot of the ones that were kind of flooding the market. So as sunstones come out of Ethiopia, you can imagine there is just cause for folks being very concerned about their validity and integrity and whether they really exist. But GIA put out a paper about a year ago now to try to figure out off the bat, how do these compare to known sunstones? And what you can kind of see is that the yellow, which is from Ethiopia, basically overlie green and blue in a lot of cases, which represent Ponderosa and then one of the mines in the southern area. And then you can also notice that the red in a lot of cases is kind of on its own, and these were some of the copper-bearing feldspar that were never really had a known origin. So I bring this up because, whether or not these Ethiopian sunstones exist is controversial. And here are some of the pictures of sunstones coming out of Ethiopia. And the fact that they have a picture from the host rock I find pretty interesting, although this picture on the right that was taken from the Sunstone Mine in Ethiopia, we really don't see anything quite like that in the CRBs. So it could be that, in a lot of flood basalts, there is assumed to be a root. We call it the layered mafic intrusion. That's where that LMI comes from. And those are often rich in metals. So if this is something that is unique to flood basalts, the next question you also might want to think about is like, well, the copper could be from this layered mafic intrusion that's rich in metals at some depth. So to highlight and kind of just finish up and kind of show you that, okay, so Oregon has sunstones. They're hosted in the CRBs, specifically the picture gorge. There's discrepancy with ages. We don't know if they formed, if the copper went in magmatically or hydrothermally, but in the youngest flood basalt, where Ethiopia is the second youngest flood basalt at about 30, and some of these other regions, China, Tibet, where the sunstones, there are flood basalts nearby, but they were found actually in alluvial material. And to be honest, these sunstones that were eventually determined to be bogus, some people have said, like, well, maybe there were a few and someone just tried to, jump the gun and monopolize on that. So I have a lot of questions about this, kind of these other locations, but, especially with just general uplift of the Tibetan Plateau, you kind of wonder, maybe there were some sunstones in those flood basalts and they've been incorporated into alluvial deposits. That is definitely jumping to conclusions, but things that I've thought about. So in summary, and I definitely went a little bit over and I apologize for that. Sunstones really have only been identified in flood basalts. The CRBs are backyard flood basalt. The youngest is really the main locality. And they're recording just this really cool process. And, it could tell us something about how even basalts that host big plagioclase are mobilized. And I think there's a lot of other questions that can be considered. But just a couple pictures. Bottom left, this is me and that PSU undergrad, Stephanie Welch, with the owner of the Dust Devil mine, Don Buford. And one over is the Hannah mine, and this is Dave Wheatley. Bottom right, John Aldrich at the Dust Devil, the Double Eagle. And then in the upper right, this is me with one of the owners of the Ponderosa mine at the American Gem and Trade Association show in 2019, just before COVID hit. So it's been kind of cool to not only see how, they extract these from the ground, but then also see them, faceted and sold to various jewelry companies. And that's all I got for you. So thank you for hanging in. I know that was a lot of listening.
Yeah, thank you, Emily. That was a great talk. There are a few questions in the chat if you're up for that.
For sure.
Going back to when you were first kind of generally talking about the CRBs, Gary asked, is there any correlation between picture gorge sites at which you took samples and the respective elevations? What can we learn from a 3D spatial visualizing of the data?
Yeah, Gary, that's an awesome question and one that I am very fond of, but I feel I always am nervous going to bat for it because I feel like I have a bunch of small lines of evidence and each one isn't super significant, but as when you combine them, to me, it tells a story. And basically that is some of the oldest, at least the most robust, so the best basically, oldest ages I have are almost a kilometer higher in elevation than some of the younger picture gorge lavas. And if you think about that, and think about the fact that picture gorge south of kind of the mapped extent is not, you don't have these nice stratigraphic exposures. And I showed you one picture of a dike, but a lot of dikes south of the type locality, the only reason we see them is because there's a road cut. And so the dikes of picture gorge in the type locality will stick out like shark fins in right around especially like picture gorge proper. But as you go further south, instead of being a shark fin, it's just flush with the ground surface. And so if you didn't have a road cut, you would literally never know there was a dike there. And so if I think about the fact that these dikes are kind of, lopped off, and we don't have nice stratigraphic exposures. And yes, some of these older ages are a kilometer higher in elevation. I absolutely, to me, it's starting to point to this area. And when I say this area, I kind of mean just some region kind of south of John Day, north of Burns, has been uplifted and significantly eroded since it was emplaced. I have tried making this argument in a paper that I submitted, and it doesn't always go over very well. Again, because some of these things are, they're, each one is kind of, it suggests, but none of them are a nail in the coffin. So I think we absolutely can learn something from that 3D visualization. I just am trying to figure out what that other line of evidence will be to confirm potentially that there's, the reason we don't have a lot of beautiful outcrops is because there's been a lot of erosion since, uplift and erosion since these things were emplaced. I don't know if I answered the question well.
The next question came from Clay, and I think that you may have covered this after he entered it, but maybe we can circle back to it. Might there have been two mantle plumes erupting next to one another to account for the overlap in ages of the pitcher gourd basalt and Granron?
So two plumes, and I will say I'm not a geophysicist, but sort of geodynamically having two plumes that close together would be pretty difficult. And I don't think there is evidence of that elsewhere kind of in the world. However, something that I will say I've briefly thought about and done almost zero research on is what if, and I mean, some people to some degree have talked a little bit about this, but what if the plume was kind of split in half? So instead of having two plumes, you really had one plume that was kind of like, sheared in some way. And people have talked about the plume being sheared, but more to your point of, being sort of bisected enough that you actually had two initiation locations is, I definitely don't know enough about that to speak to it, but I would say that would be a more likely possibility than two kind of distinct plumes. And also when, I didn't mention this before, but with plume, sometimes you hear plume and hotspot used interchangeably, and technically they're not exactly the same thing. Hotspots more represent sort of anomalous volcanism, and plumes also represent anomalous volcanism, but there's a connotation where that plumes connect to the deep mantle. So when you use plume over hotspot, you're kind of saying that you know something about source and that it has kind of a deep tail. So then again, thinking about two plumes coming off the deep mantle that would be challenging, but I think there absolutely is, reason to think about, how could the plume be sheared such that you had kind of two potential plumes kind of interacting, or two portions of the plume interacting with the crust.
Yeah, thank you for that explanation. That's interesting. Crystal asks, this sounds very much like a subduction or uplift. Are either of these possible? And could these two locations have been closer at one point, the two sunstone locations?
Yeah, they definitely could have been closer, but I wouldn't say more than like, I don't know, maybe like 20% closer, because there is a lot of the Brothers Fault Zone to some degree kind of intersects the space between the two. So it is definitely possible that they could have been closer together, but knowing that they're 80 miles, I would say, maybe like, and this is really back of the envelope, like maybe 60 miles, but I really think that would be pushing it. So yes, I think potentially that northern mine was uplifted, but not so much that sort of as the crow flies, that it would really influence how far apart they were.
Okay, and Paul is wondering what eliminates sunstones forming in basalt vugs like zeolites?
Yes, this is definitely a question that has come up before. Typically within sort of basalt vugs, right, they're vesicles, and so they're more circular or like sub-rounded to some degree. And sunstones, for the most part, they don't have kind of that round shape. And to form the temperature of plagioclase crystallization, trying to get that temperature at the surface after the vug had formed would be exceedingly challenging. So I think between that, the shape of the crystals versus typical vesicles, and I don't think it's something like that's been documented elsewhere in the world. Some people have proposed that, but I can't wrap my mind around how it would happen.
Because these are feldspars. Are the crystals faceted?
Sometimes, so when they come out, depending on the kind of integrity of the rock itself, sometimes they're like beautiful euhedral plage, and in sometimes, especially like in the northern mine, and anyone going on the field trip will definitely see this. There are certain outcrops of basalt that have really coarse plage, not visible copper. And those are, I mean, you can see cleavage planes kind of reflecting at you from as soon, the sun hits the rock, and it's like, oh my gosh, it's beautiful.
Thank you. These are so much weirder than I had imagined.
They're bizarre.
Let's see, Charlie has a question. Shouldn't there be a concentration gradient from the diffusion of copper into the sunstones from China? This should be a clear giveaway of artificially treating the clear sunstones.
Yes. So the work that was done for kind of determining the fake sunstones, I was not part of that. That was done in the early 2000s. But the problem, and this was a problem I ran into when Stephanie, the undergrad, did her work, is that measuring copper at concentrations, because even though you can see the copper, what happens is if you slice that crystal in half and you go to analyze it, unless you're on a copper flake, basically, the copper concentration is actually really, really low. And the methods by which we can get like elemental concentrations at that scale, copper, the detection limit of the instrument basically isn't low enough to measure. So it seems like kind of an obvious thing to do is like, oh, just measure the copper across the crystal. And it's actually really difficult with the precision of our analytical techniques. An electron microprobe, for example, the detection limit doesn't go low enough unless you're on a copper chunk. Basically, it doesn't go low enough because, it kind of sucks because you want the scale to be small enough so that you can get changes. But because where that probe is analyzing is so focused, you're not getting like a bulk composition. You're getting just, a little spot. And so it's actually really, really hard to measure copper concentrations across a sunstone. And when I have done it, it's been bulk. So I've crushed an entire sunstone and then got the copper concentration of the whole thing. And when you do that, it's typically up to about 300 parts per million. And that's just not high enough for a probe typically to measure. There are other methods, but then you start getting into really kind of basically instruments that are more expensive. There's fewer of them and they're more expensive, and it's harder to pull favors to get people to get some data.
I was just going to say that there's microprobes that use crystals, wavelength dispersive, and you just broaden the spot and just slowly go back and forth a couple of times to develop a pattern. Even also, you can cut the samples into a thin film, and therefore you're not getting any variation underneath it. So you have a thin film and you're just going back and forth with a broad beam. I grew up as an undergraduate in the electron microscope lab at University of Michigan, so I have helped maintain it as my.
Oh, cool.
And so we always wind up with extra nuts and bolts when we put it back together. But they would have these crystals, and then you just move your sample back and forth underneath the beam with a broad beam, and also make the sample very thin, so you're not getting any variation from underneath the spot. So those
Yeah, that's oh, sorry, keep going.
Well, that's a common thing, for geologists. I've known them. Maybe they all retired.
Do we have any more questions from the chat?
Yeah,
Oh, sorry, go ahead, Emily.
oh, I was just gonna say but the point I think with Charlie. Oh yeah, Charlie, your question. It's been more. I don't know if it's been kind of made more sense in terms of time, but one of the ways that they really figured out that which sunstones were kind of not real was that they would basically collect argon isotopes, and if they were treated, then that means they were heated up, and so they lost all their radiogenic argon, and that was the primary way it ended up being, I think, the strongest and the quickest way to figure out, especially for like a lot of samples at one time, if the sunstones had been basically heated recently. But to kind of loop back, one of the things I'm now thinking about is that's kind of a problem that we're running into with the real ones, is that they've lost some of this radiogenic argon and they're giving us these younger ages. And so it kind of makes me wonder, those sunstones that were deemed kind of rubbish and the copper inclusions weren't real. If we're solely relying on lack of radiogenic argon and the real ones actually do lack it for whatever reason, that argument tends to, I think it's still there, it just maybe isn't as strong.
All right. Just a quick thing, going back to Clay's talk, you may have a plume that splits, and then the plume can pick up different chemistries depending on where it's coming up through the crust. That could give some differences in chemistry. I think referring to Clay's earlier comment.
That is one of the reasons, that actually exact kind of point is one of the reasons. So Picture Gorge has what we call, in some places, this metasomatic signature, which basically just means it's enriched in like specific elements that are sort of fluid mobile, thought to come off the subducting Farallon slab at one point. So absolutely, if you have these two different chunks of the plume, and one is interacting with more pre-existing mantle that had these kind of metasomatic signature, absolutely, it could be sort of inherited and then become part of the signature that erupts. And to be honest, it's something I think is absolutely valid, because if we think about Picture Gorge being the earliest, then it would kind of make sense that the first stuff coming out had kind of like clearing your throat, right? Like in the morning or something, you know, that first kind of couple times you talk, you're, you know, you might be like kind of hacking up a lung or something. And kind of the same thing for the picture gorge, you know, there's this other stuff. And once everything was kind of established, you end up producing basalts that have more of a uniform geochemical signature. It's one idea, but
Very colorful.
Let's see, Paul is
yeah, maybe
wondering-
that was a gross analogy.
Still good.
It made sense. Paul is wondering what the research and funding prospects are for this work. Well,
Paul, you're lucky that this question is coming this week and not last week, because if you asked me last week, I would have, I mean, I'm still kind of clenching my fists, and I'll hold my tongue because this is being recorded. But after waiting far past the deadline, I found out last week that NSF declined my funding. It was considered, basically got, from all intents and purposes, as far as I can tell, like as close as you can get with not succeeding. So that is a bummer. But so that's the downside, right? Bad news first. Good news, there may be an avenue for me to pursue this in the next year, but it's not going to happen overnight. It's going to take probably, you know, another 6 to 9 months. So the immediate prospects, I'll tell you after I got that email, I took a shot of whiskey and I worked out for 45 minutes because I was so angry. But it looks like there might be another way to pursue this, but so that's kind of the intermediate news. The good news is that, and this may open some doors, who knows, is that I'm working with the producers of OPB's Oregon Field Guide, and we are doing a show. We're filming the end of August. So while that doesn't yield funding, it does yield sort of exposure, right? Science communication, and I'm hoping that kind of might help. And brand of whiskey, to be honest, I don't even think it mattered. I think it was Pendleton, though.
Well, we hope that someday you're able to get to Ethiopia or China and continue the work.
Me too. Me too.
Well, just be sure to read through. There's lots of kudos in the chat here for you, Emily. I think everybody really enjoyed that talk. So thank you so much.
It's exactly what a geology
Thank
talk
you.
should be, that brings the theory and the narrative down to something so concrete and beautiful. So thank you.